Hello.
Hello?
Yes. So today we will discuss about the today we will discuss about
Hmm.
the magnetic potential. You can
Hmm.
recall in electric field while we were studying the electrostats, we discussed this concept that electric field can be expressed as negative of the potential gradient. So means electric
Yes.
field in terms of electric potential as a its negative gradient. Yes.
Hmm. Yes, sir.
So here this V was the electric potential.
Hmm.
Similar to the that this H can be expressed as negative of the scalar magnetic potential, right?
Yes, sir.
So H is equal to negative of delta, H is equal to negative of delta Vm, where M for the magnetic, this Vm is magnetic scalar potential. Okay?
Okay, sir.
Okay. But problem here is that unlike problem here is that unlike the electric field, this scalar magnetic potential is not valid at all cases. This is having these certain limitations. Let us try to
Hmm.
understand what is that limitation. So if
Hmm.
you take the, for example, see, if you take the curl on both sides of this equation, so I will write del cross H is equal to del cross minus of del Vm, right?
Hmm. Yes, sir.
Yes. And there is an identity which I have not means, told you previously, but here you can remember, and you can also check it by taking any one example of your own. That
Hmm.
curl of gradient is always zero. See here, very very carefully. This is a very one important identity. I'm telling you, this is a means universally accepted identity. You may take any function, you may take any scalar quantity. Take its, for example, just I'm giving you one example. Suppose you take x square plus yz plus z cube. This is a scalar
Hmm.
function.
Hmm.
You take its gradient, means del of y. I hope you know how to take the gradient.
Yes, sir.
Yes. Then you
2x
take,
plus.
yeah, so you take its gradient, just I'm giving you example,
Hmm.
just you take its gradient and then you take the curl of this gradient, put a negative
Hmm.
sign, or you may not put the negative sign, even if you don't put, then also if you take the curl of this
Hmm.
del y, this
Hmm.
del y is a vector, yes or no?
Hmm. Yes, sir.
Y is a scalar, but del y is a vector.
Hmm. Hmm.
You can recall, I have told you that the gradient of any
Yes, sir.
scalar is always a vector, yes or no?
Vector. Hmm. Yes, sir.
Yeah. So curl of this gradient is always zero. You may take any function,
Okay.
you may check it. Whenever you are free, whenever you wish to check it, you may check it for a practice that curl of gradient is always zero. So
Hmm.
now the what is the problem? Means we are saying that okay, this curl of gradient is zero. This we know, or this we have already used. But we have studied, and that's why I asked you, and we have studied that del cross H is J. Yes or no?
Hmm. Yes.
And here you are getting, for this scalar potential, you are getting del cross del
Hmm.
Vm is equal to 0. Yes or
Hmm.
no?
Yes.
Then means it's a very problem. And what you are writing, this minus of delta Vm is what? This is nothing but H, because we have defined here. You
Hmm.
see, this is nothing but H.
Hmm.
Yes or
Hmm.
no?
Yes, sir.
So in equation 1, you are writing del cross H is 0. In equation 2, you are writing del cross H is, sorry, in equation 1, it is del cross H is J. In equation 2, you are writing del cross H is 0. So
Hmm.
left hand side is same. So should be the right hand side? Yes or no?
Mm.
Yes. So this is the ambiguity. This is the limitation. That which one is true? Either this one is true or this one is true. And if both are true, under what constraint, under what limitation, both can be validated.
Okay.
It simply means that if I wish to say that okay, this function exists, means the scalar magnetic potential exists, then there must be J should be zero. Then and only then this is valid. Yes or no?
Yes, sir.
And what was J? If you can remember, the point form of Ohm's law, J was sigma times E. While we are
Mm.
discussing the current, I told you that J can be expressed as sigma times E, and this is known as point form of Ohm's law.
Mm.
So J is sigma times E. So for this J to be zero, sigma means charge density. So if charge density is zero, then only this can be zero.
Yes.
Now try to relate. If the charge density is zero, means it is a space, it is a charge free region.
Yes.
Means no charge is there, no current is there. So, but of course, no magnetic field is there. No magnetic field is there means its curl will be zero.
Yes.
I mean, this is a very limitation that we are considering this a scalar potential valid only when sigma is zero. Try to understand what I am trying to emphasize. That this scalar
Okay.
potential is valid only for the charge free region, not for all region.
Okay.
You're getting my point?
Yes, sir.
See here, we define a scalar magnetic potential. You see the statement with a condition that Z is zero. J is zero means
Mm.
sigma is zero. And sigma is zero means it is a charge free region,
Okay. Mm.
like in free space only. Free space
Okay.
is a charge free region. What I
Mm.
am trying to emphasize since last few minutes that this scalar magnetic potential, like the electric magnetic potential, in electric magnetic potential there was no such constraint, but a scalar magnetic potential is bounded by a constraint that this is applicable or validated only for the charge free region. Am I
Yes.
clear till this point?
Yes, sir.
It means this is not a very means good potential. So we need to define the one more magnetic potential, and which should be applicable to all regions. That should not have any restriction. And what is that
Okay.
potential? That is known as magnetic vector potential. In magnetism, you may say that there are two possible potential. One is the scalar, just like this. E is negative of the gradient of V, H is minus of delta Vm. But once again, I am repeating, this is having the limitation. What
Mm.
limitation? Limitation that it is applicable for J is equal to 0 only. Yes or no?
Mm. Yes, sir.
Yes. So J is equal to 0 means for the free space. So I
Mm.
need to deal with some other potential which should
Mm.
not be with this, and this is the our other potential, that is the very important magnetic vector potential. Very
Mm.
important because this is applicable for all case magnetic vector potential.
Mm.
Okay.
Yes, sir.
And especially as you are means having the interest in electronics, on that day you said, sir, I'm having the interest in electronics, and yes, I asked you why to do PG. So did you think over it?
Yes, sir.
Yes.
Mm.
Yes, hello.
Hello?
Yeah. On that day, while interacting, we were discussing that why to do PG. So,
Yes, sir.
so did you get the answer of that? Yes. What?
So 1 minute, sir.
Sorry.
1 minute, please.
Why? Hello. Hello.
Hello?
Oh,
Hello? Yes, sir.
yes. So, did you get the answer of that?
Uh, um, Nothing, sir. I was thinking that I want to be an engineer, so I should know things properly.
Mhm.
So
Do
with
you
B
think that
Tech,
why means in PZ you will be knowing the things much better?
yes, sir.
Okay, okay, fine. We'll talk about this later on. First, let's see. Electromagnetic potential. Now let us come to the topic. So, as already I said that a scalar magnetic potential is not valid at all points. So, we are going for the one more potential, that is the vector magnetic potential. So, now see the concept here. Another important point I am going to say. See, this we have studied. This is known as which law?
Goes slow in magnetostar.
Yes. And what does this indicate? What is the physical significance
Means
of this law?
uh,
That it simply means that magnetic field has neither source nor sink.
physics.
It means that magnetic field lines have neither source nor sink. They are continuous in nature. You have forgotten. Yes or no? Hello? 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 Left out हो गई लगता है. Hello.